Hello. Hi, I'm already seeing some comments. Hello, Aki Bean, and hello, Pro2. When is the stream starting? The stream is already on. But I noticed the last stream just ended like 3 minutes ago. So you can just take some time to catch your breaths, have some water, and we can get going in the next 5 minutes. Hi, Vandred. Yeah, so in the next 5 minutes, I'll just introduce us to what we are about to learn today. So take some time, relax, take some fresh air, some water, and we'll get started in the next 5 minutes. While we're on that, how have your day been? You can just drop a comment, tell me how your day has been, and how is it going? How is the challenges coming up? How is the stream so far? And don't forget to sign in. You have the barcode right there on the screen. And I'm also dropping the link on the comment section. So you can go ahead and check in for the stream. I see a question already. Incident for resource quota or security incidents. Incidents in general, infrastructure specifically. Okay, just before we get started, small chats. How have your day been? How's the challenges coming up? I hope you're having a great time with the challenges, and I hope you're having fun at the same time while doing that. Okay. So welcome again to the Global Hack Week. And today we are going to look at why cloud systems fail, right? So why cloud systems fail. We'll be focusing on generally what has been going on, systems failing. Sometimes you sign into your favorite applications and they're no longer working. So we'll take a look at all of that. We understand why they fail and how we can actually build our systems, to actually resist, basically to build our system to be resilient, right? So we can actually promise 100% non-downtime of system. So no infrastructure platform promises 100%, right? So the system is always going to fail. I mean, over the months, we have heard big infrastructures like AWS fail, even Google Cloud and Azure. So no one says they are not going to fail. So they will fail, but we'll be looking at why they fail and how we can actually build our system to withstand, failure. So we're actually not going to build system that will not fail. So nobody promises that the systems are not going to fail, but we'll see how we can actually build so that the system can resist total, downtime. So my name is Vincent, and your Major League Hacking streamer for today. Now let's actually take a look at what we'll be learning: cloud incidents, outrages, cascading failures, and then how we can actually design so that we can actually recover fast and also reduce blast radius when systems fail. So we'll take a look at all of that. And now there's something many people don't realize, and even the biggest cloud infrastructures in the world, they fail. I just mentioned that a few seconds ago. Like AWS, Google Cloud, Cloudflare. I think Cloudflare fell some months ago. So these are like big cloud platforms, and they all fell at some point, right? So the interesting part is it's not about the failure, but it's why they fail and how they manage the failure when they fail. So which is what we'll be looking at. Nothing technical. We'll be just having a conversation and understanding how the systems are being built and how they withstand failure and how you can also think from a reliability engineer perspective when building systems, right? 3 months ago, last year December, so I gave a talk on one of the Google Dev Fest events, and one of the quotes I used during my session was, the topic was literally about building systems that withstand failure. And one of the quotes I used was, "Don't let your Vera moment becomes your failure." Right? So I'll just expand on that a little bit. So there's a lot of AI, vibe coding going on. So anyone can actually spin up an application. You can just build. You can literally build anything these days using AI, which is cool. But then you need to build with assumption that the system will fail, right? So always build with assumption that systems will fail. That is the best way to build. So when you build with assumption that the system will fail. So let's say in your campus, you're building a platform for your department, for example, and let's say you have like 1,000 people in the department. And when you build application, you build for just 1,000 people, traffic, database, the storage, you're building for just 1,000 people because you're building for your campus. So what happens when someone from your department tells someone else from a different department, or someone else from a different school about the application or about the platform, and at the same time, everyone is using it. So initially you build for 1,000 people. What happens when 10,000 people are using the platform at the same time? So you will notice that the system will fail because you build with assumption, or you build with what you have, which is the data you have of 1,000 people. You didn't make provisions for what happens when the system fails. So we are going to take a look at, why systems fail. I just give you a scenario of why a system fail, just a very example of why system fail. Building with assumption of, okay, this group of people are going to use my platform, but what happens when you have more traffic than you expected in your platform? Okay. And I want to make this stream very lively and interactive. So I'm going to ask you questions. I want you to, give me your opinion why you think systems fail, why large cloud systems fail, why do you think they fail? Like examples of why you think they fail, your personal opinion, or why you think cloud systems fail. Sometimes AWS fail. Why do you think they fail? Okay, it's a reason one. I was involved. Okay, that's funny. Okay, so other people I know were involved. Okay, Tinder, continue. Probably the product owner also was involved. Amazing. Okay, and because AI was involved. Okay, that's all for the responses. But yeah, you were involved somehow. Okay, and other people also were involved somehow, and also the product owner also was involved somehow, right? I mean, these three first answers actually correspond with the example I gave. If you build for a small system, with the assumption like 1,000 people are going to use the platform and 10,000 people use the platform, so you're involved. You that use the platform were involved. Other people that use the platform for the 10,000 that was not included in the 1,000 are also involved. And lastly, probably the product owner, because he built uh, he built just for 1,000, but then we had 10,000 people, so he too was involved. So those three answers are actually valid. And yeah, AI was also involved because maybe they vibe coded, right? Midnight, they vibe coded and they didn't think about system design. They didn't think about reliability. So they just vibe coded and just, deployed. And yeah, boom, something happened along the way. So yeah, AI also was involved. Okay, so overload usage spikes. Yes, too much traffic. Again, you build with the assumption of 1,000 people, but then you have 10,000 people. So that's like an overload of what you have built for. So it's a simple mathematics. This car can only contain 4 passengers, and then how would 10 passengers trying to enter the same car that was built for 4 passengers? So there are gonna be issues, there's gonna be congestions inside the car and so forth. So overload spike. I had to go down to the basement and replace hard drive 3 Christmas in a row. Fun fact. Let's read the fun fact out loud. So, fun fact from Tinder. He said, I had to go down to the basement and replace hard drive 3 Christmases in a row because of crashed drives. So I decided to move to the cloud. 2 months after the big move, Azure had a worldwide storage service outage for 8 hours. Yeah, okay, that's a very fun fact. Yeah, and yeah, no, I will not say it has happened to me. Yeah, like moving locally to the cloud. Yeah, but I have clocked into work one time at my company where I work. I've clocked into work and Cloudflare was down, and Cloudflare was literally powering our front end. So, which is the initial interface the user see to actually use the feature or the product itself. So, we couldn't do anything because we depended on Cloudflare for that. So we literally it was like I think Cloudflare was done, AWS was done. So it was more like a no working day because nothing was actually working. Customers There was actually no way even customers to actually reach out. So we were using intercom. So customers need to reach out through intercom. And I think intercom also depended on AWS. So there was actually no way for customers to reach out. There was actually no way for them to use the product. And there was also no way for us to even communicate. I think it was also affected Slack. Yeah. So it was literally you just log into your system, nothing is working, you just rest. So this is reality check. It's going to happen. It has happened. and it will continue happening. But yeah, we're just going to look at how we can actually build systems that uh, how we can actually build systems that are resilient to this, when these things happen and recover fast and so forth. So AWS Azure was down for like 8 hours. That the storage service was down for like 8 hours. That's a lot of hours, but I think it has happened. And funny enough, it could be a physical disaster that made it go down, right? So again, these things are going to happen because we live in a world where earthquakes are happening and we can't do anything about it. But we can build, a resilient system that we can. Okay, if an earthquake, take cover, make sure you don't get hit and so forth. Ways we can prevent more damages, but we are just not going to avoid every single thing. There, natural disasters and stuff that could still affect the cloud. So when we just say the cloud, we're not talking about something magical. It's a physical data center that people are seeing. There's security guys there minding, the data center, and anything can affect it, right? That could be fire outburst and so forth. So anything can affect it. Okay, so all right, the users, no problems. But then there's a product without users. How is it going to work? Got you. Okay, still reading the bad hammer. Step one, let's build biggest distributed platforms ever, where everything is built to not take anything else down. Step one, let's put 90% of the network behind a single point of failure. Yeah, still, it's just like the way your body works. Your legs need your hand, your eye needs your brain. So at the end of the day, it's all microservices. So everything needs each other. And when we build systems that doesn't need each other, what happens? The waterfall methodology, right? If it fails, it fails. Boom. And that's even the worst part of it, right? So microservices actually, when it was introduced, we went from waterfall to agile, which involves microservices to make it easy when systems fail, so that the whole system don't collapse. So if you lose your left hand, you still have your right hand. Yeah. So we can't just have systems that just depend on itself 100%. You can build everything, right? Yeah. I mean, you can build everything. Okay. Oh, so this was literally what they did after the long 8 hours of Azure going down. Interesting. Yeah, 8 hours. That's a very long time. Like businesses are going to lose money and all that. So again, it's real world. And when these things happen, the stock market goes down for some companies. Users get frustrated and so forth. So all valid answers why large cloud systems fail, right? Again, it's not magic. It can happen. It will happen because it's bound to happen. And because it's all microservices, when it affects one, it affects most of other platforms that depend on it. So AWS goes down, let's say Discord goes down with it, let's say Stripe goes down with it because they all maybe are hosting their infrastructures in AWS. But there's always a way they recover. So we'll also take a look at that throughout this session. Okay, so this is basically where reliability engineering matters a lot, right? So if this is the first time I'm hearing about reliability engineers, can you let me know in the comment section? Reliability engineering, sometimes they develop engineers DevOps engineers, reliability engineers, cloud engineers. Sometimes they share things they do, like they have something in common, right? Even though some just focus on CI/CD. Okay, example, cloud DevOps engineers could just focus on a specific stuff, which is maybe making sure of CI/CDs, continuous integration, continuous integrations, and so forth. Uh, I mean, that could be just all they focus on, but I mean, there are organizations that just have DevOps engineers. They also do the work of reliability engineers. Also, companies that have reliability engineers that also do the work. Literally, they're all interconnected, right? You can be a full stack engineer, you be the front end, back end, and every single thing. So basically, it's you can do this, do that. But let's take a look at why reliability engineering matters, right? So when class systems fail, it isn't just a website that stops working. Uh, a lot of things behind the scenes stop working, right? So if you build a system and you're collecting payment from Stripe, and let's say you are hosting your application on Google Cloud is active, but AWS is down. And let's say Stripe itself hosts, their infrastructure in AWS, right? Automatically, your payment gateway stops working, but every other part of the application still works, but the payment gateway stops working. Yeah, it happens. Unless you have like alternative payment gateway that I've implemented, right? Just in case something happens with this specific payment gateway, alternatively, you can use this other payment gateway. But then, if they all depend on the same infrastructure, again, obviously they're not going to work. So again, why when systems fail is not just that the website is not opening; it could be it's opening, but some part of it is not working, right? And real check, reality check, businesses are going to lose money. Streaming stops. If you're watching maybe something on Amazon Prime or Netflix, or you're listening to music on Spotify, businesses lose money. That's actually the most impactful part of it, because people are going to lose money. Uh, Developers are going to panic. Yeah, developers are also going to panic. It's trying to find a way to solve the problem. They're on the hot seat. Your managers is on you. These are your responsibilities and so forth. So everybody's on the hot seat. I think we have a situation like this at work where uh, our platform went down for. It's not like it totally went down. So a specific feature was not working. We have a distributed, team. Some in US, some in America, some in Europe, different time zones. I remember vividly. It was like 2 a.m. Eastern time. We have to wake up the staff engineers to take a look at. So we have something in place, right? We talk about things you actually have in place just in case things like this happen, right? So it's not like someone is calling you on phone. You already have things automated to actually monitor and alert you when things happen. So I mean, everybody, it was off working hours, like 2 a.m. in the morning. These guys have to come up. They have to come into work and they start looking at what the problem is, find the problem, fix it. So developers panic. No, but you don't need to panic if you experience and you know what you're doing, right? You just be calm, look for the problem. But yeah, there's does be that pressure of trying to get a system back up because the company is losing money and people are opening tickets. Why is this not working? So a small mistake in distributed system, can affect millions of users in seconds, right? So if your platform is like a shopping, an e-commerce that people order, pay money, order fulfilled, and you're using Stripe, for some reason Stripe is down, so people are trying to order, but they can't order and they can't pay. So you're losing money at that moment. If they look for alternative platform that maybe they're not using Stripe, they go there and do the shopping. So a small mistake, could just affect the whole system and company lose money and so forth. So it happens. That's why engineers don't just design systems. Or that is why you too should not design systems assuming everything will work. I think I mentioned that earlier. Don't design assuming everything will work. Design assuming things will break. Like your first mindset when you want to design is this will break, but what can I do when it breaks? So this is literally where reliability engineers come in. Think like a reliability engineer. Designing for failure ensures reliability, right? So clouds is not magic. Again, it's not a magic world. It's a physical hardware. Right? So the first time you heard about cloud, you can tell me what came into your mind. You can just drop it on the comment section. The first time, in your entire world, you heard about cloud computing or cloud engineering. Like, what really came to your mind? What was the first thought? Now, not when you actually figured it out what it was, but what was the first thought, right? Again, it's not a magic word. It's not something on the cloud, up there. It's somewhere down here without. It's something. It's a data center, just like the way you have a physical machine. Your physical device. You can actually build a data center in your house. Well, maybe a very small one with a cooling fan and all that. Pretty expensive, but you can. But then it is still a physical center. So it is not magic. It is not, invisible. It is visible. So at the end of the day, it's a complex system. Different a data center. They have all the whole hardwares networked all together and how it communicates to each other and so forth. So it's complex. So understanding the nature of the distributed system actually is literally a way you can actually build so that if there's failure, that could be a backup, right? I love to use whiteboards. So let me see if I can draw on the screen. So this is literally a flow of a cloud architecture and how cloud works. I mean, I could just spin up a auto draw here and try to draw, but I think the diagram also makes sense. But yeah, I love to draw. So let me spin up. Let me just draw a little bit right here. Where are you? Let's see. Got this right here. Okay, so let's actually take a look at like a standard system architecture of how a system basically works, or a cloud architecture of how it literally works. Let me take a look. So first is like a user. So just use this as a user. And pardon my drawing. So this is a user. A user makes a request to, yeah. Before we just dive into the whole logic and jargons and keywords, let's just take a look at it like from a day-to-day activity. So you have a person that wants to come to your house, right? So this is your friend. Your friend comes to your house. This is your house. Pardon the house, but it's a house. So for your friend to come to your house, your friend needs your address, right? So again, this is a user. Okay, if I can write, I can just write right here. So this would be a user, literally. And this would be what we refer to as DNS. Oops. How do I drag you? That spoiled my house. Oops. Okay. I'll just leave it right there. Yeah, but these are DNS. Okay, so when you hear DNS, I want to give you like a real life example of what is it like, and how it works. So it's using the same analogy. You know, there's a user, there's where they want to access, which is like this house. Then this house, they come to this house, which is fine. I'm not sure this is gonna work because you want to visit your friend. You have your friend's address. Your friend gives you the address. You visit them. What happens next? You guys just have fun, maybe play video games or see a movie, and it ends there. Yeah. So this is not gonna work. So let me use a better example. Okay, let me use a better example of visiting a website. So the first time you visit a site, what you're doing is this is a browser. You are visiting the site. You are the user. This is a user. Just make it very tiny. This user is visiting this website. So when you visit the website, basically what you're visiting is what we call a DNS, right? What's the DNS? What's the full meaning again? Can anybody help me out? Distributed network. Someone help me complete it without looking at the internet. Anyone? Okay, so let's look at the internet. So it should be distributed network system or domain network service. Oh, yes. Domain name domain name, yeah, domain name system, domain network service. Yeah, I think it's domain name system, literally. It's basically like a phone book, right? Just like your house address. So it's just a name. Yeah, so domain name system or domain name service. So it's literally every single website you visit has a unique IP address. So the fancy domain names you see, like Netflix.com, like Google.com, behind the scene is an IP address attached to it. So when you visit the website, you're literally calling that IP address, which is the network. So that's what happens when you visit the site. And something happens when you visit a site. It either loads fast or it loads slowly, right? Let me give you an example of this loading slowly and loading faster. What is actually happening? So that's what we call CDN, content distribution. It can be content distribution network or content delivery network. Yeah, any of that works. Still means the same thing. That's CDN. So when you visit a site, it's either slow or it's fast. If it's slow, maybe there's no CDN behind the site. If it's fast, there's 99% assurance that a CDN is behind the site, right? So CDNs are like cache. It's a cache memory. And they are also the reason why someone in the USA can watch some type of movies on Netflix and someone in UK can't because it is not available in their region. Yeah, CDN also helps with that. So a website's being faster, it could be slow the first time you visit it. That could happen depending on the content of the site, right? If there's no CDN, that means every time I want to visit this website. So example, I want to visit Netflix.com, and Netflix.com is hosted somewhere in US East, right? Let's take that for example. This is hosted in US East 1, literally using Netflix as an example. So each time I want to visit Netflix, I am making a call to this IP address, and what happens is it goes all the way, it travels, the latency, the time it takes to travel from wherever I am, let's say I'm in Africa, or let's say I'm in Asia, or I'm in Europe, the time it takes to travel from my location to US East 1 could be, let's say, 10 seconds, right? The first time I'm visiting the site. If there's a cache memory, if there's a CDN behind the site, what happens is next time, if I want to visit that site next time, what happens is if I'm in Europe, or let's say I'm in Africa right here, right? So let's say I'm in Africa, somewhere in Africa, and I make this request, and it goes all the way to US East 1 and returns this back to me. Why returning this back to me? What it does, if there's a CDN, now I'm trying to explain what CDN is. Content distribution network, content delivery network. It could be any of that. So what CDN does in this case is it looks here. So this is using AWS as an example, right? AWS as an example of where this website is hosted. So if I make a call from Africa to this website, it goes all the way to US East 1. It brings back, the data I have requested. If there's CDN behind the scene, it looks here in Africa. If there is a data center closest in Africa, right? So if using Africa as an example, AWS have a data center in South Africa. So what it does is it finds a data center that AWS owns in South Africa, somewhere here, right? It stores a copy. So it's like it copies, a data, the same, the whole information I make the request to, it copied a copy of it and paste it here. So if, I visit the sites in the morning, finish whatever I want to do here, log out. So the next time I come back here to visit the site, two things happens. It actually looks for the copy here because it will be faster. This could take me maybe 3 seconds, right? Instead of 10. So this will load faster for me. So it will look if there's a copy of this data here. If there is, then it just gives it to me. That is why sometimes you visit a site, the first time you're visiting it is very slow. The second time you're visiting it is very fast. It has CDN at work. So it has stored a copy of the site, the data, in a location, data center closest to you. So that next time you're visiting it, it serves you that copy, which is very fast. So this is what is happening. But you may be asking, since it's a copy, what if this data has been updated? So it does this. It checks also before it starts this. It also checks if the copy here and the copy here is identical. If it is, fine, no problem. But if it's not, it redirects you back here to fetch the updated data and then installs a copy here. So this is CDN at work. So this is literally what CDN does. So when you configure CDN on your applications, this is literally what is happening. Okay, so we have like CloudFront. Yeah, AWS CloudFront is a CDN network. Is it CloudFront? Not sure if it's cloud. If AWS has CloudFront or Azure, I've forgotten which of them has CloudFront. Yeah, not sure. Let me be sure. I think it's AWS that has CloudFront. Yeah, CloudFront is actually an AWS service. Yeah, Amazon CloudFront is a kind of CDN service, right? That actually helps you, deploy your services or applications. Yeah, it's AWS service that helps you deploy your services, closest to the edge technologies or edge data centers closest to your users. Okay, I've forgotten Azure own. I think it's something dull. Let me confirm. I just type Azure CDN. I think they'll just give me the name. What was it called? Oh, it's called Azure Content Delivery Network. Yeah, they just use the whole full name. I think it was renamed. I think it used to be something Door. Not sure, but yeah, they just call it Azure Content, Azure CDN. Yeah, that's the short call, Azure CDN. Yeah, these are all type of CDN services that can actually help you, uh, implement CDN behind the scene. So moving forward from this is like a typical cloud diagram. When you try to design a system, this literally a system that is resilient. The flow or what should happen and how you should set it up. Okay, so this in place, fine, right? Then we have a guy we call the load balancer. I'm trying to, yeah, I think I know exactly uh, what to use as a diagram for it. I'm trying to figure out what I can use. But let's see. I can use a shape. Mm, Let me use this guy right here. Yeah, yeah, something close to that. We have this guy, and this is literally a what they call the traffic police. That tells you when to go and when not to go. Yeah, you can actually call load balancers. Yeah, traffic cops. You can call load balancers traffic cops. They tell you when to come because they know the road is clear, and they tell you when to hold on, not to come. So yeah, we can actually use traffic cops as load balancers in this example. So this is what is happening. When you build your site and you implement load balancer behind it, you're literally giving it instructions on what to do. I mean, it's automated, so it's not like you are there looking after it. It does its job based on what is happening, just like a traffic cop. A traffic cop knows when you should hold on and when you should move so that the car coming from north or south does not jam the car coming from east or south. So that is the work of load balancer. It monitors and controls when something should happen in your infrastructure. I have a question. I'll just get to that question until I finish this. I'm already going to go back to the question. So when you say AWS Elastic Beanstalk is a LEB Elastic Beanstalk is a reverse proxy service or forward proxy service. Not pretty sure I got that question correctly, but Elastic Beanstalk is a pass. Oh, Elastic Load Balancer, not Beanstalk. Sorry. Okay, so Elastic Load Balancer. So we say is a reverse proxy service or a forward proxy service. So what's the difference between reverse proxy and forward proxy, if I may ask? GD mailing. So what's the difference between a reverse proxy and a forward proxy? Like, I want to know the difference between both, if you know. So I'm not sure. Like, I'm not sure of the answer to this question right here, but we can actually do a little bit of research on that, so we can know the difference between a reverse proxy and a forward proxy. So a forward proxy acts on behalf of clients, that is users, to access the internet. Okay, enhancing privacy and filtering outbound traffic. A reverse proxy acts on behalf of web servers, sitting in front of them to manage incoming traffic. Yeah, so I think that answered the question. I think it's literally a reverse proxy, not a forward proxy, because it is going to manage traffic and does what it's supposed to do, like provision more virtual machines or more storage or more RAM and so forth. So it's literally a reverse process. So it's acting on behalf of the web server instead of acting on behalf of clients. Okay. So I think the key difference is for your question is the target audience. Like forward proxy serves client, forward proxy serves clients, while reverse proxy serves web servers. And in this case, it's literally web servers, right? So I mean, which both of them actually, hmm, both of them actually, uh, both of them actually contributes to when load balancers actually works, right? I mean, this is what I mean. 10 users accessing a site that was built, 10,000 users accessing a site that was built for 1,000 users. If there's no load balancer, it crashes. So again, there is forward, like users interacting, and then if there's no load balancer, so that means there's nobody to actually take a job, like do the job when the web server is overloaded, and what should happen next. So, but yeah, to answer your question, I think it's actually a reverse proxy because it's monitoring the web server itself, what is happening done on the web server, not the users. So users overloads the web server, the load balancer acts on the web server that has been overloaded. So if the storage is, let's say, reaching 80%, it spins up another one. So it's acting based on the storage, like that storage, which is the infrastructure. So not literally on the users that is coming in, but then they all contribute to each other. The users contribute to overloading the server, then load balancing, acting on it. So that is like a literal example of what load balancers do. So it monitors and does its thing of, if I initially have this website for 1,000 users, you're welcome. And then 10,000 users are visiting it. So if the storage initially was a gigabyte and it can only occupy, or it can only contain 1,000 users, and now 10,000 are coming in, that means maybe I need 10,000 gigabyte. So what load balancer does is it monitors when this is near 80% or 70, based on whatever you design it to do. And if it is close to that, it spins up another storage. It spins up another storage and adds to your infrastructure. So that from a gigabyte, you now have like 10, so that your system never goes down. So that is the whole idea. So from this guy, which is the load balancer, we can now have like our application servers. We can now have our application servers right here. Your Node.js engines, Apache, and the rest of them. So we can have them here, which is the engines that now power your applications as well. You have databases and storage all, down here and down here, and they're all part of the infrastructure itself. Yeah, this is a rough drawing, but it explains the whole flow. So user DNS, CDN, if there is one, load balancers, application servers, database, storage. So all of them. Again, these guys, if you just take a look, I put them differently because we are looking at building a system that can actually be, dependent on its own. They don't depend. So they're independent of other systems. So like your storage should be on its own. It shouldn't be inside the same virtual machine that is housing your application. So it should be on its own. It should be on its own. Just in case this fails, it shouldn't affect this. It should building a distributed system actually makes the work easy, so that if one fails, the other doesn't fail. So this is like a rough drawing of the whole process of a system architecture that can withstand, failure. Not that it can withstand, not prevent failure. But there is more to this, right? Inside here you can see have different availability zones. Where you have you can also have multi clouds, but these are expensive. Like the more you want to build a system that is actually very resilient, the more expensive it becomes. Example, there are companies. So I was work as a contractor with Vodafone. So I think their infrastructure they're using multi-cloud. So they have AWS, they have Azure, and I think they're using Google Cloud at the same time. Three cloud at the same time, right? So that's like multi-cloud architecture. We are just in case AWS goes down, they already have a standby server, like a replicant of everything they have on AWS on Azure, for instance, or also on a Google Cloud. So if this is going down, this is up, because there's never going to be a time the whole AWS, Azure, and Google Cloud are all done at the same time, right? So they definitely not going to be done at the same time. These are all different data centers, so there's no way all of them are going to be done at the same time, because they're different companies, different infrastructures, different regions, different locations. So that's multi-cloud, but it's expensive, right? You are paying for this, and that. So the more you want to build, close to 99%, it can never be 100, but the more you want to build like close to 99%, the more money you can spend on it. Okay, let's go back to our slide. So the drawing I showed was a rough diagram of what it looks like and how a system architecture actually works, which is also here on the screen, like the flow. User initiate requests, DNS resolve domains, CDN delivers the content, load balancer distribute traffics, application processes the data, database stores information, storage, retrieves the files, and so forth. So let's actually dive a little bit into what are incidents, and focusing on cloud incidents. Literally, an incident is anything that can disrupt a system, right? That's an incident. So any event that disrupts a system is an incident, right? So there's downtime, latency, partial failure, because it's not 100% failure. That is why we have distributed systems. So it will never be 100% failure. Some parts are working, some parts are not working. That's why it's distributed. So it's an incident. So not every incident means the system is completely done. So it could be the login is not working. It could be the payment is not going through because that particular infrastructure that helps you with the payment gateway is down. It could be images are not loading because maybe the images are loaded are coming from Cloudinary, and for some reasons Cloudinary server is down. So usually what that means is your images will not be loading. So there are benefits. So there are benefits to distributed networks. There are also disadvantages of it, but overall, I think they are better than waterfall systems, because waterfall systems are disaster. If it fails, they all fail. So again, I will always go with distributed networks. So I don't know. Can I want you to give me examples, like examples of real incident examples, real world incident examples that you have come across, in your day to day college work, while building your personal projects, your applications, your startups. Like, give me real incident examples that have happened. Like, tell me your story. Like, I'm looking at it from the comment section. I want to hear your story of when you experience a real incident, when you experience a cloud incident, something that disrupted your workflow, something that disrupted your work, and how you actually overcame that. So tell me your story on the comment section. I think I already told the story of what happened at work sometimes. So system went down, and but we have to. It was not working hours, but we need to come up and fix the problem. I mean, examples could be API errors, API error spikes, maybe, and the API starts giving you 400s codes, bad requests, 500 servers down, and so forth. So, and nothing is working at all. It could be traffic failing. It could be service restarting. I mean, if a service is restarting and your platform depends on that system, it have to wait for the restart to finish before it can continue whatever it's meant to do. So if you have examples of a time that you have experienced an incident, let me know on the comment section. Looking at the comment section for your story. Yeah, so that's I'm literally looking forward to your stories if you have any. But if you don't, yeah, we can go ahead. Okay. One thing I just want to mention is why building, right? Why building systems that last. You know, this topic is all about why it fails. If you understand why something failed, you can be able to build a system that helps you to recover fast when it fails. So, which is the whole idea. And one thing that is very important, and every serious organization does this, is monitoring, right? Is monitoring, right? Monitoring. I think I did a stream sometime last year on monitoring. I think it's also on cloud. Yeah, I talked about monitoring, observability. There's a word used. I mean, observability is like you're observing everything, both good and bad. You are just not waiting for the system to fail before you react. You're observing when it's good. You're observing when there's a spark. You're observing when there's no spark. Like, there's a monitoring system in place. If, let's say, your organization works, like, communicates on Slack, then have a Slack channel where you are logging in every system alert, whether good or bad. It helps you monitor the pattern. Maybe during a rush hour, when the system there's a lot of spark, and you're like, okay, this is when you have more sparks from this region or that. So my point is, monitor everything, like monitor every single thing. And let's discuss yeah, cascading failures. So this is literally, in a distributed system, failure rely system. So in a distributed systems, failures really stay isolated, right? So what I mean is, a cascading failure begins with one component failing. So it doesn't just happen. It doesn't happen like the whole system collapses at the time, right? It could be database performance, performance degradation. It could be increased requests in the queue. And this is a literally example of what is happening, right? Database is slow, for example, uh, and there's an API that depends on the information from the database. So if the database is slow for some reasons, and I'm making a request, another user is making a request, let's say 5 people are making requests at the same time, but database is very slow. Because it's slow, the requests are not being fulfilled on time. So the API, that means database is performing very slowly. The API that is waiting on the database is waiting. So now that we're having a waiting here in our system, right? The whole APIs are waiting. That is request queue, you know, piling up. And what happens is the server start getting overload, right? Because different things waiting at the same time, the system, they're getting overload, and then the entire system just crashes. So this is like a example of a cascading failure moment where one component of your application is having issue, but it affected the rest of the endpoints that depends on that particular application or that particular component. So database is having issue. Database is the only service that is slow. But because it is slow, requests are not being fulfilled on time. There's an API that is waiting on it, and it's something that's supposed to finish in a second. It's finishing maybe in 20 seconds or more. So the more we have more waiting API calls, the more we're having a request queue on the system, which is overloading the system. When you spin up your system to play a video game, if you play video game with your system, and maybe your system is not designed for video game, and you spin up a video game, you can hear the sound of either your hard disk and your GPU making behind. If you listen, you can hear the sound because you're overloading it. You're giving it more work than it was designed to do. It may not crash, but it may also crash, right? If maybe it gets so overloaded, maybe it's not in a cool environment, it may crash. I've actually had a system crashed on me before. Yeah, like I was literally on my PC, and I heard some funny sounds. It was spiking, so the board was spiking. I can hear the sounds, and the system just went down. There was a bit of smokes coming out of it. Yeah, that was literally back in the days in college. But yeah, this is a little example of how cascading failures happens. So failures, if they're not literally, they don't just happen. It's one system that starts, maybe other system that depends on it, and the whole system gets overloaded, and everything just fails. So understanding blast radius in system, so good architecture limits blast radius effectively. So when we talk about blast radius, we're talking about build a system that when it fails, it has the smallest server impact, right? The single server failure should be a very tiny impact. It should not affect. It shouldn't have much of an impact in the whole system, right? So there's a small impact, medium, large. There's a massive impact, like a global impact. So the goal is to make sure that if something must fail, it should be at the minimum. It should be, the smallest of it. We should be able to recover fast. We should be able to, spin up something for a backup. So great engineers design systems to limit blast radius. So build so that it's going to fail. Like I mentioned earlier, systems are always going to fail, but the goal is to build so that we can minimize and then the time it takes us to recover from the failure. That is the goal. And just before I go ahead, if you uh, so again, this session, this stream is not technical, it's theoretical, just learning about how these systems work. But I have a stream coming up tomorrow, and it is going to be all about, it's going to be technical. We're going to do some uh, technical stuff, which will cover some of the theoretical things we have done today. So this is like setting you up for designing, a system. Okay, so failures, I think that is basically what we'll be talking about all through. At beginning of the stream, I asked for examples of, what causes big systems, large systems to fail. We have a lot of examples, and yeah, it could be a small mistake. It could be that engineer forgets to, you know, configure that endpoint, that configuration perfectly fine, and it's just a little mistake, and that broke the system. It could be software bugs, which could also be a configuration mistakes. It could also be dependency failures. I mean, literally every system depend on the other. So again, dependency failure. I'll give you example, a real world example that could happen. Your system depends a lot on maybe some npm, uh, some npm packages. So that's a dependency. For some reasons, the person that manages that npm package, made some mistakes or deployed some changes. Again, your system is fine, but because it depends on maybe that other system, and that other system has a bug that is causing a problem, you see your system having a problem, right? So that's dependency failure. So it can also be traffic spikes, too much traffic than expected. It can also be network issues. And sometimes human error as well, right? So sometimes human error. Maybe something happened in data center, and someone that's supposed to check on the cooling system forgot to, maybe something happened. It's there's fire outburst, and the whole server, that particular server went down. That affects your system automatically. So it could all happen. These are like things that happen. So everything we'll be talking about has been why system fail and how we can actually design to build, resilient systems as well. So you learn how the thing fails. You build a system that helps you to recover fast. So one is, redundancy to ensure backups are available, right? Uh, Again, redundant is not cheap, right? But yeah, that is like multiple servers. You have multiple servers, just in case this server is down, the other server can spin up immediately and so forth. You have isolation to contain failures, like separate services. I gave an example earlier where you have like a payment gateway on your system, let's say Stripe. But what happens if Stripe is not working? You can have an alternative payment gateway also, just in case this is not working. Then you can try this, so that like isolation, you know, isolates the services. They shouldn't be too dependent. You shouldn't just have one. So you should have like separate services that can spin up, that can be used when this is not working. Then importantly is monitoring, right? Monitoring for early detection. So detect problems quickly. And I mentioned, don't just focus on detecting problems. Focus on also detecting, when things are working smoothly. In the past, I used to I used to have like a manager, like way back in the past, uh, that only looking for when you make mistake, right? Like They're just waiting for you to make a mistake, and they will come for you like, "Hey, you didn't do this well," But nobody gives you thumbs up, when you have been doing things well on the way, just waiting for you to make a mistake, and they're like, "You see, you didn't do this way." So, but all this while you've been doing this way, but no one is giving you, accolade. So my point is, don't just wait, don't just react when it's failing, or don't just build monitoring systems only for failure. Also build to monitor, when the services are all working fine. So fall over, yeah. So that was like building backup systems to take over just in case. This is literally where load balancing comes in. We have, you can have different regions. You can have different availability zones, availability regions. They can spin up just in case these services are not working. You can have different services. Let's say you have this server. You can have the database living in this region and also have it, a replica of it in another region. Again, it, it costs money, right? If I'm having this service here and I'm also having a copy of it in another place, that means I'm paying for both of them. And the goal is I'm building with assumption that this will fail. If it does, I want you to connect to this other region for me. So again, it costs money, which is what it is. So backups, backups cost money. Yeah. When you have like a backup car, you have two cars. If one fails, you can take the other one to work. It's money. You have two phones, just in case this one fails, you can take the other one. You can use the other one. You have, two laptops, just in case one fails. So backups definitely gonna cost money. So failover always have like a failover. So systems, when companies, startups build systems that withstand failures too. So failover is part of the business plan, because the architecture design, because you don't want your system to be down because something failed. You want, if it's done, redirect me to somewhere else that is working. Okay. And then lastly is graceful degradation, right? So system still works partially, even though it's done. I think late last year, after AWS went down, I think a week later or days later, X, former Twitter, also went down for some period of time. But if you notice, if you log in, you'll be able to log in. You'll be able to log in, but you are not able to see, like recent tweets. It was like a cache. So some part of the system was working. So that's like a graceful degradation. It is not a total failure. It's not like you try to log in and you're visited with, fail for not found. So it is some parts are working, some parts are not working. So also design in such a way that, even again, that's what microservice is all about. Like the whole system does not depend on, one dependency or one system. So like if this fails, these other things are working. So that's like a grateful degradation. So system still works partially, even though it's done. I was going to draw, but I don't think there will be need for drawing. So I think I already explained that, like when you have a resilient architecture where you like different regions. So we can actually incorporate different regions in our drawing earlier on, where you have US East 1, US East 2, and you have the same services you have here, also here. Just in case US East 1 goes down, you can spin up US East 2. So it can be 3, it could be 2, different regions. Again, that's cost money, more money as well. So it's like having the same server in 3 different regions. So you're paying for the same thing, but 3 times because they're in 3 different places. So I think the key takeaway is, cloud systems will fail. Again, they will always fail. but that's not literally weakness. It is reality. It's happening. It has happened, and it will continue happening. So the goal of engineering or the goal of reliability engineering is not to eliminate failure, right? Uh, I don't think there has been any hospital in the world where there have not been a failure. That would be a lie. If the hospital can boast of 100%, you know, rate of success in treatment, in maybe in surgery, now, that would reality check, in as much as we're in the world, there will never be 100% non-failure. So we can't eliminate failure, right? But we can design systems that survive failure. So that is literally the goal of everything we talked about today. Why systems fail. Of course, they will always fail, but what we do just in case it fails, so we can recover from it fast. We can actually build systems that survive the failure. And I think that brings us to the end of our stream today. And we're here for questions, personal stories of when your system failed, and any other thing you want to share or questions as well. Let me know. And while I'm waiting for questions, I'll be dropping the feedback link on the comment section, and I'll put it right there on the screen. So let us know how the Global Hack Week has been going so far, what we can improve, the streams you have enjoyed, any feedback from the streams also, like something we can do better to make the experience more better, and any other thing you want to share. So you can go ahead and fill the feedback link. Okay, so I have a question right here. It say, do you have an idea of why recently there has been many cloud outages? That's a very interesting question. And honestly, I have no single idea. So every company will give a report of what happened. And I mean, honestly, it has not been like the problem affected other services similar to that particular platform. For example, when Cloudflare failed or when Cloudflare was not working, other services like other competitors of Cloudflare was also working. So I think again the problems are all personal. Or it's all peculiar to them, like why it failed. I mean, they always release report of what happened and what we have done to solve that problem. There was a joke on Twitter. I think Elon Musk when Cloudflare. Sorry, no, yeah, when Cloudflare or AWS failed, I think AWS lay off some engineers and replaced them with AI. And Elon made a funny comment, like, oh, this is where the AI is working because the system failed. So it could be a bug. It could not. Basically a bug, misconfiguration, something. Maybe it could even be the AI itself, that wrote some code that broke some production uh, code. So yeah, literally, any of that can happen. And remember, these systems are very complicated, right? It's not like it's a very small system. It's very complicated code base. So maybe they all depend on each other, and every single tiny mistake, every single tiny push, you know, every single tiny release breaks the other systems. So it happens. So at work too, that this has happened, right? We released the feature, and it broke existing feature that was working perfectly fine before. Yeah. So again, the issues are just peculiar to them. Why it happened. It could be a coincidence that it's happening. Maybe they all happen within a period of time. Maybe AWS went down the next day, class the next week or so. Cloudflare went down. This other service went down. Yeah, could be a coincidence. Could also be uh, they're sharing results that they all depend on, right? Maybe there's a result. Okay, I think last year or sometime last 2 years, uh, there was a system failure, like literally system failure in the whole of Africa. And yeah, the whole of Africa. What happened was, uh, I can't remember the story, but yeah, it was a cable, like the cable that crossed from the river over to the other side in the Red Sea have some issues. That's a physical disaster. So most of your data centers are living under the water, just so you know. So like Azure, most of the data centers, their fibers, they're all under the water. You know, I mean, these are they need to be because they're very hot. So something like that can happen. So reasons recently there has been cloud outages. No idea if there is a specific reason, but there are reasons peculiar to them. Yeah. So yeah, this 2024, last 2 years. So the last 2 years, right? This 2026. Time flies. Yeah. That happened. Like literally a whole lot of services in Africa went down because of a single giant cable that had some issues somewhere in the Red Sea. So I was relating to this story. Like okay, let's say that's 2024 when this happened. Literally every service was having this issue, right? Like every single service, in as much as we are this side of the world, every single service that depends on that giant cable was affected, whether you're AWS or your Azure or your Google Cloud, everybody was affected. So maybe because they are sharing the same resource. Yeah. So if AWS is done, Azure is done at the same time, and maybe it's specific to a region, maybe there is something they are sharing within that region, that have issues. So that is maybe literally what happened. Yeah, the shark, the shark attacked it. I think we still have like about 5 minutes to go. If we have questions or anything at all we want to discuss, but if we don't, we can call it a day, and we can catch some break, and let's see what we have next. I think whatever we have next will like in the next 2 hours or so. Let me check. And don't forget the feedback link right there on the screen and on the comment section as well. I just dropped that again. Yeah, I think our next stream will be on hardware. So if you are interested in, robotics, Arduino, hacking hardwares, yeah, you should check that stream out with Bully. So you'll be giving you insights on hardwares and robotics and how to build your mini hardwares at home. I have a question. So, do you think future cloud platforms will move towards self-healing infrastructure that can fully recover from failures autonomously? And so first of all, so I was reading, the first line. Do you think future cloud platforms? And something came to my mind. I was like, how many years have AWS and Azure been? AWS, Azure, Google Cloud. You know, yeah, I think we have IBM. I mean, the most three giants, like the big three, AWS, Azure, Cloud. They have been, they have been here for decades, and I mean, they still haven't solved this problem. I mean, even with the whole, quantum computer, even with the whole I mean, literally, to be honest, AI actually cause more problems when it comes to failures now. Like things are actually easily to fail than before. I mean, before humans are writing the code and humans are reviewing the code, right? But these days, AI are writing the code. AI is also reviewing the code. So uh, AI made some mistakes because they can make mistakes. Yeah, the whole system fails. Like what I'm trying to say is systems are actually easily to fail more now than before, because honestly, it's like the more we go, the more we have more system failures, like more class system failure. Like the more advanced things are becoming, the more fragile things are becoming as well, right? Because if a human is writing code, I think like the faster, the more fragile. If humans are writing the code or doing these things, it's a little bit easier to move slow. When AIs are doing it, they move very fast. So what that means is if they're moving too fast, something can also fail too fast. So to answer your question, I don't think so. I don't think future cloud platforms will move towards self-healing, because most of the things that cause cloud failures, some are things they can't control, like natural disaster. They can't control that, right? So that aside, in as much as we can write code, we can always make mistakes. Like there is no 100% way somebody may not make mistakes, right? As a human, you're bound to make mistakes at some point. So even the most cracked head engineers, sometimes they make mistakes. I mean, AWS fair, right? They have like crack engineers that handles these infrastructures as well. So human errors cause this. Self-healing, again, if for the that self-healing, if I highlight it, and if you're referring to maybe using AI to self heal it, again, is a prompt, right? Basically AI is being prompted on what to do when this happens or when that happens. What if it is something outside of their own scope? What if it's something outside of the prompt? So they can only try, but it can never be 100% self-healing, right? It can never be 100%. It could try to recover, but some things may be unrecoverable. It could be a physical disaster. It could be a human error that also needs a human intervention. So they could try, but from what I've seen so far, it's like the more advanced tech is becoming, the more fragile it is becoming as well, which is very obvious. It seems monitoring and testing will grow. Yes, it will. It has always been there. I mean, that's literally how you notice when something is wrong. Because, so I'll just give you an example. We have a Slack channel at work. That Slack channel is dedicated to monitoring. We have one that it's his job. We're logging the monitoring logs right there, like the database sparks, traffic, and everything. I also have systems set up in case uh, specific issues happen. Alert this team, stuff like that. So yeah, 24/7 alert system, because that's the only way you can actually know when something is wrong and when something is happening. Okay, I think that stream should be in the next. Let me see. That's the stream on Adreno. In case you're interested in what's it called? Robotics, hardware, hacking, and stuff. I think that will be in the next 2 hours. So you have enough time to rest and join the stream. Again, pasting the comment on the comment section, the link to the feedback link. So go ahead and let us know what we can do better. Okay, if there's no other question, I think we'll call it a day. And yeah, thank you all for joining the stream. And if you have questions, the Discord is right there. You can drop any other questions you have directly to me if you want to ask me a direct question. Thank you and see you tomorrow. Adios. And that's bye in Spanish. Yeah, have a great day too.